This video is going to cover section 11.5, which deals with equations that are reducible to quadratic. So, equations in a form that can be treated as quadratic for solutions, or also radical equations and rational equations that we can look at as quadratics for solution. Okay, and they involve substitutions. So equations in quadratic form we can have ones that aren't really quadratic if they can be solved in a quadratic way. The example they give here is that the square of x squared is x to the fourth. So x to the fourth minus 5x squared plus 4 is a quadratic equation if your variable is x squared. To make a little more sense out of that, say you let u equal x squared, then your equation would be u squared minus 5u plus 4, which we recognize as quadratic. So there's all what I just said with the u substitution. So that means that it's reducible to a quadratic, or we can call it in quadratic form. There's some kind of substitution that we can make that will make it into a quadratic equation that we can solve as a quadratic equation, and then remove the substitution to solve for the original variable. So here's an example. The x to the fourth minus 5x squared plus 4. Well, we're going to let u equal x squared. And we're going to then solve by putting u in for x squared and u squared for x to the fourth. Now, how do you know what you're substituting? It really is a matter of trying to force that first term to be something squared. Okay? So if you take the square root of that first term, that'll tell you, and just the variable part of it, that'll tell you what to set u to make this substitution. Now, it's only going to work if you have that variable expression that you're using for u as your variable expression in your second term. You'll get used to these and seeing how they work. Some of them are complicated, but most of them are fairly straightforward. So we get u squared minus 5u plus 4 equals 0. You could complete the square on this. You could use quadratic formula on this. You can do all kinds of things. The easiest thing to do with this is to factor it. It's such an easy factoring. U minus 1, U minus 4. So the principle of zero products tells us we can break those up and set them equal to 0 when we get u equals 1 or u equals 4. Now here is the caution. You're not done yet, because you've solved for u, but your original equation is in terms of x. So now you have to take this substitution equation and substitute your two u values in there to solve for x. So you'll get x squared equals 1 or x squared equals 4. And now when you solve those, you'll get plus minus 1, plus minus 2. You get 4 solutions, which you should expect from a fourth degree equation. You check them both. But as it notes here that because of the squaring, 2 and minus 2 are going to check the same, and 1 and minus 1 are going to check the same. So we only need to make 2 checks. And there are the checks that we put in. to see that they're both true statements. So there are indeed 4 solutions: 1, -1, 2, and -2. So again, be careful not to just solve for u and then forget to solve for x. Always look back and see what your original variable was. Okay, so the basic idea here is that we're going to look at the variable expressions in the equations and make sure that one expression is the square of the other. You can only use this if one variable expression is the square of the other. And then write down your substitution, solve that way, and then go back and solve for the variable that you substituted for. And check all the possible answers in the original equation. Some may not work. So sometimes you're going to get rational equations, radical equations, exponential equations with rational exponents. They're all reducible to quadratics. And these are the ones where it is absolutely essential that you check your answers. Because remember what happened when we were doing rational equations, radical equations, sorry, that some of them didn't check. Because they were being squared, and that kind of masked out the minus sign, and when you checked it, it didn't work. So here we're going to solve for x minus 8 square roots of x minus 9. Well, what do you think we're going to do with that? X is the square of the square root of x. So what can we substitute for u? We can let u equal the square root of x. And when we substitute, we're going to get u squared minus 8u minus 9. Again, simple factoring. U minus 9, u plus 1 equals 0. U equals 9, or u equals -1. Now we have to substitute back into u equals the square root of x. So either the square root of x equals 9 or the square root of x equals -1. So x equals 81 or x equals 1. Now we must check. And when we check the 81, it works. And when we check x equals 1, it does not work. And the reason is because this is not the principal square root. And when we take it here, we have to take the principal square root. So we only actually have one solution to this. The only solution is x equals 81. Okay, how about this one with negative exponents? We are going to let u equal t to the -1, because t to the -2 is the square of t to the -1. And when we substitute that in, we'll get u squared plus 4u minus 2. This is not factorable. So we're going to have to use quadratic equation on it. Minus b plus or minus b squared minus 4ac all over 2a. See, we've put all the numbers in here. A is 1, B is 4, C is -2. And when all of that work is done, your final answer is -2 plus or minus the square root of 6. And that's what u equals. But u is t to the -1. So we're going to separate these out into the two separate solutions, -2 plus the square root of 6 and -2 minus the square root of 6. And t to the -1 equals those. Which means 1 over t equals those. That's what t to the -1 means. So we're going to have to flip our solutions. 1 over -2 plus the square root of 6. Or 1 over -2 minus the square root of 6. Check those. See if they work. You should rationalize the denominators too. You shouldn't leave radicals in the denominator.